Okay, great students, this is the lecturer, Mr. Ramnath. I'm just going to give a short presentation on how you could possibly use GNU Octave for your mechanics courses in the old qualification or the new qualification. So for the purpose of this little video, I'm just going to show you how you would use it for a vibrations problem in some of the upcoming assessments. So let's just see where we are. So let's suppose we have a mass connected to a spring which is fastened to a wall, and the mass is displaced by some distance x because of some force. In any case, the equation of motion is minus kx is equal to mx dot dot, which can be written as mx dot dot plus kx is equal to 0, which in turn can be written as x double dot plus omega n squared x is equal to 0, where omega n is equal to the square root of k over m. And of course we need to solve that, and from mathematics the solution would be of the form x is equal to a sine omega n t plus b cos omega n t, which for certain conditions would have different values of the constants a and b. So let's say let's consider the following boundary conditions or initial conditions. Let us suppose, for the sake of argument, that x is equal to x1 when t is equal to 0, and the velocity is equal to v1 when t is equal to 0, where the velocity is just the time derivative of x. Using that information, we would have that the displacement x would be v1 over omega n sine of omega n t plus x1 cos of omega n t. Okay, so that is the equation. Let's consider that to be the equation that we want to solve. Now, of course, you could solve it manually with pen and paper. However, in the various assessments, it's probably going to take a very long time for you to solve all the problems by hand. Okay, so how would we solve the problem on a computer? Well, in this course, I would prefer that you use Gnu Octave, and there are two different ways you can use GNU Octave. You can use it with inside the program itself, or you can use it with a notebook. A notebook is basically a web browser in which you can run Octave, and there are some reasons to do that, but I won't go into the details. So how would you run GNU Octave in a notebook? Within your computer, you would go to a shell. In this case, I'm going to use Anaconda PowerShell. I'm opening up a shell. Shell in Windows is basically in MS-DOS. Let's wait for it to run. Okay, so in my computer, that is my computer's name. And if I want to open up a notebook, I would just say Jupyter Notebook, press enter. And it should open up a web browser in a moment. Computer's a bit slow, but that's fine. Right, there we go. It's setting up a server. The server is now talking to your Explorer, your web browser. In my case, I'm running on Windows 10. My default web browser is Microsoft Edge. Edge is now talking to the server. The server is now creating a local host, and we'll just wait for it to load up in a moment. And there we go. And then, well, these are my documents on my computer. I then say I want to create a new. In my computer, I have Julia, Octave, Python, and R as kernels. So I'm going to select Octave as a kernel. It will now open up a new file, an IPython notebook inside the web browser. So this is what's called a Jupyter Notebook. And this is my local host and server. And if I want to write some text, this is my computer program to solve the problem. Right. I can put bold fonts and italic fonts and so on and so forth. Now, let's go back to our problem. We have a mass, a spring, we want to work out the values, and we have some initial conditions. So let us, inside the web browser, put in the mass and the value for the mass, the value for the spring, and let's run it. So that will give me my natural frequency. Then I want to put in some initial conditions, time at 0, a value for x1, time at 0, a value for v1. So let's just say, for the sake of argument, x1 is equal to 0. Let's say 0.030 millimeters. V1 is equal to, let's say, 62 millimeters per second. 62 millimeters per second. Then the constants, that would be the formula for the x as a function of time in terms of my parameters. So let's suppose I want to plot the solution. I want to plot the solution for t. Let's say n is equal to 100 points. T is equal to equal points from 0 to, let's say, 1.75 seconds, and I want n points inside there. Then I want to work out the values for x. X is equal to v1 over omega n. So x is equal to v1 over omega n times sine of omega t, sine of omega n times t, and then plus x1 times cos of omega nt plus x1 times cos of omega n times t. Right, let's run that. We run the program. Let's just save the notebook. Great. And then I want to plot the results as a function of time. I will then say plot t, comma, x. Let's make it a red line. Show the grid. Put in some labels. T in units of seconds. Y label. Displacement x in unit of meters. Put in the legend. Solution. And put in a title. Graph program. Let's run it. So when you have the star, it means it's still running. We'll wait for it to run in a moment, and there's our solution. So what do we see over here? Our equation is a mass, a spring, and a damper. It is in form x double dot plus omega n squared. X is equal to 0, and we basically realize that this is simple harmonic motion. So that is simple harmonic motion. Simple harmonic motion. Something double derivative plus something times the zero derivative is equal to 0. That's the equation for simple harmonic motion. And when we look at the program and the results, that's exactly what we expect. Something goes up and down, the spring is going upwards and downwards, which is exactly what happens. We deflect the spring, it deflects, then it's pulled back, then it goes back, and so on and so forth. In this case, there's no damping. So this is how you'd use a GNU Octave program inside a Jupyter Notebook. So I'm not entirely sure if you're allowed to use Jupyter Notebooks in the exams and the test, but let's suppose you're not allowed to use it. So if you do want to use the program, you can also use it directly as a program itself. So inside GNU Octave, you would open it up. Okay. while it's running. So this is the program. You'd go into the editor. You would just write your computer code. I'm just going to copy it. Then save the file. Then you would then run the file. And there you go. So there are two different ways of doing it. You can run your GNU Octave program inside a notebook, inside a web browser, if you want to, or you can just run it directly inside the GNU Octave program. I think it would probably be easier if you run your computer program inside the GNU Octave program directly instead of the notebook, but it is entirely up to the students how they wish to do it. And that would be the end of the video. Thank you very much.